is number effect indeed. Can that large be overall of events are very events? No, of predictable, which such the occur with yet very unpredictably.
Dr. Hume just told you what this film is about. He wrote a sentence to explain what we want to show you. And then he cut the sentence up into individual words, put the slips of paper into a hat, and drew them out in a random order, and read them to you in this random order. Here's the sentence before it was scrambled. Random events are events which occur with no order, that is, unpredictably. And yet, the overall effect of a very large number of such events can be very predictable indeed. Who's going to start?
Well, let's use a random event to decide. Heads or tails?
Tails.
Heads, you lose, you start.
Here are random events occurring naturally. See the needle? Hear the clicks? This is a Geiger counter, and this contains a radioactive material, polonium. Every time the Geiger counter clicks, it means that an atom of polonium has changed into an atom of lead, except that there are some extra clicks because of cosmic rays. I said that these clicks are random events. What does that mean? It means that there's no order to them. I can't predict when the next one will occur. Even if I measure the time between clicks very accurately for a large number of clicks, I will still not be able to predict when the next one will occur. That's what I mean by a random event.
Here's a picture from your textbook. A graph of the activity of a sample of polonium plotted against time in days. You can see that the activity, that is the number of radioactive disintegrations in the sample, decreases as time goes on. The activity at the start is 100%. It's only 1/2 as much at the end of 138 days. At the end of another 138 days, it's half of what it was at the end of the first 138 days. It's down to 1/4 of its original activity. And this goes on. Every 138 days sees the activity cut in half. This length of time is called the half-life of polonium. All radioactive substances behave in this same way. Some have very short half-lives. Here's helium-6, a radioactive isotope of helium. It has a half-life of 0.8 of a second. Some have very long half-lives. Here's uranium-238. Half-life is 4.5 billion years. As you can see, if a graph of activity is plotted in terms of half-lifetimes, it is identical for all radioactive substances. This is a law of radioactive disintegration, a description which fits the behavior of a great variety of substances and allows us to predict their activity at any time in the future. How can this predictable behavior emerge from the random, unpredictable behavior that Dr. Ivy showed you? Well, we'll come back to radioactivity later, but first we're going to investigate some other examples of random behavior.
Would you care to predict where the next marble will go? The same place? No. I'll try a few more. Unpredictable, isn't it? There are 100 marbles in here. I'll drop them all. that's the slot that the marbles are most likely to go into. I'll mark the way that the marbles are distributed here. I'll put the marbles back in the tube. Now I'll do it again. You can see that the distribution is not going to be the same. This time, there are most marbles in this slot. Perhaps now I might guess that the marbles are more likely to go into the slots here, but that's all it would be, a guess. I still haven't made enough observations of the behavior of this apparatus to make reasonable predictions about what will happen. So I'm going to take some statistics on the apparatus. That is, I'm going to observe what the behavior is in a systematic way. I'm going to drop 100 marbles many times, and each time draw a graph like this of the distribution. And Dr. Hume will help.
Well, let's get to work. Here are the 10 distributions we found in 10 tries. You can see that they're all different. I'll put 3 of them together so you can compare them. Now you can see the sort of fluctuations that there are between them. This graph shows the next thing that we did. We added together these 10 distributions, and we divided by 10 to make this graph the same size as these graphs. This is now the average distribution for the 10 tries. One way of looking at this is that this is the distribution we would have found if we dropped 1,000 marbles all at once in the apparatus, except that we couldn't because the apparatus won't hold 1,000 marbles all at once. Then we did this again. Dropped 100 marbles 10 times. We got another 1,000 marble distribution, and once more. There it is. These 3 are 100 marble distributions, and these 3 are 1,000 marble distributions. You can see that the fluctuations here are much smaller than the fluctuations here. If we dropped 1,000,000 marbles at a time in the apparatus, then we probably wouldn't be able to see any fluctuations at all. Each of these graphs is a frequency distribution, and the point of taking a lot of statistics for the apparatus is to get the best approximation that we can to the true frequency distribution for the apparatus. The average of these 3 will be reasonably close to the true frequency distribution. Here it is, the average. Now that I have this, I can make predictions, statistical predictions, about the behavior of this apparatus. You can see
that the frequency here is about twice that of the frequency here. This means that the probability of a marble going in this slot is about twice that of a marble going in this slot. It didn't go in either one. You must realize that a single marble still behaves unpredictably. To say that the probability of a marble going in here is twice that of a marble going in here just means that if I drop a very large number of marbles, twice as many of them will go in here as go in here. And as you've seen, very large number means just that.
You've seen how to find the frequency distribution for a simple pinball machine. What about this machine? It has 16 squares of cardboard mounted so that they can spin around. One face is white and the other face black. Now the light scattered from these squares can be read on a light meter over there and the results projected on the screen. Right now, half of the squares are white and half of them are black, and the reading is 8. Now Dr. Ivy is going to turn the squares around so that they are all right side out.
Now?
Yes, now. We've made the scale on the meter so that it reads directly the number of white squares facing out. The reading now is 16. Now we better check up on the all black reading. The reading is 0, no white squares facing out. Dr. Ivy is going to start the squares spinning now with a fan. He has to help some of them along by hand. I want them to end up facing out, so he's sliding a screen across the back. The reading is 8. Now we're going to do this again several times and just show you the results.